Okay, I got another one. This is chapter 36, number 17. And the question asks, what spherical mirror is to be used to form on a screen that is located 5 meters from the object an image that is 5 times the size of the object? Now, maybe a good review here is important because if we take the concave mirror and look at really 3 different positions, and so if this is the center of curvature and this is then half of that, the focal length, an object that was placed here always made an image that was between these two and upside down. So it was inverted, and it was between these two, it was upside down, and it was always smaller than the original object. So that is definitely not what we want here. We want it 5 times bigger. Okay. Now, the other thing we learned is that if the image was placed, well, maybe I'll just put another image here. Another object here. But if the object was here, then the image would be out here. It would be inverted, it would be bigger, it would be real. And that really has the potential of answering this question, because here it would be bigger. And more importantly, we've got to project it onto a screen. And so we've got to actually get the light there. Because the next thing we learned is that if the object was placed here, we would get an image over here that was bigger. And so this mirror is much more interesting than the convex mirror. The convex mirror, which has its focal length inside of the mirror and its center of curvature inside of the mirror, only gave us one option. So this is more of a boring mirror. It always gave us an image that was smaller, virtual, right side up. Whereas the concave gave us the 3 different options. The object placed here was smaller and upside down. An object placed here made an image bigger and real, upside down also. And this one made a bigger but virtual. And so the only thing that's going to work for the design criteria, this is what the optical engineer would need to realize, the only mirror that can work for this design is really this mirror right here, a concave mirror, where the object is placed somewhere between the focal length and the center of curvature, such that then the image is then 5 times bigger upside down, and then this is where you would put your screen. Now, of course, we probably don't want the image to actually be upside down. So I guess the real beginning part of this is we would probably then have some kind of focal length here, some kind of center of curvature here. We would take the original object and place it upside down, so that the light that bounced off, and this one went through the focal point, and then this one went through the focal point and off the mirror, made then an inverted image, which of course is now upright because our original object is made to be upside down. And so that's really what they want here. And so that's really what A is. A says, describe the type of mirror that is required. And so A is, it's got to be concave. We cannot accomplish bigger and project it on a screen with well, we can't get bigger with convex. We can get bigger with the concave if the original object is in either of these two spots. But in this spot where it's in front of the focal length makes it virtual. You can't project it onto a screen. You can have the appearance of coming from there. So if you're using a camera or your eye, it'll look like it's coming back here. But you could not then put it onto a screen that then could reflect off for an audience to see or something. So we must have the concave. And so that's the first part of this, the type of mirror where what must be used. And then B, where should the mirror be positioned relative to the object? And again, it should be between these two locations here. And then I think we have enough information to go on and really answer the numbers, even though I think we've kind of answered that. Or, well, it says where, so I think they do want a number. And so let's try to solve this. If we go 1 over P plus 1 over Q is then equal to 1 over F. There's 3 unknowns here. What they've given us is that they want this distance here. The spherical mirror is used to form on a screen 5 meters from an object. So the screen is going to be here, and we're 5 meters away. So that is really saying that if you took this distance, which is P, and you added 5 meters to it, you would get the Q. So that's what that statement is saying. But it is also saying that the magnification would be a 5, although let's not forget we better put a negative 5. And so that requires us to understand the physics of what's going on to throw in the 5. They just say 5 times bigger. They don't necessarily say upside down, but the fact that they say it on the screen gives us no choice for that. Anyways, when we solve this, then we have a 5P is equal to a Q. So if we put these two things together, we have then a P plus a 5 equals then the Q, which is the 5P. And so if we bring that over to here, we've got a 4P, or we've got P equaling to a 5 over a 4, which is what, 1 1/4. So there's the, whoops, got it kind of off the screen there. Let me scoot it back over there. All right, so there's the value of P. And of course, then once we have the P, we can get the Q. So 5 times the P, which is 5 over 4, gives me the Q. And so the Q is 25 over 4. Let's see, 4 goes into 20, I guess 6 times, and 1 left over, so 6 1/4. Okay, so then finishing this, we can also get the focal length. We've got 1 over the P plus a 1 over the Q. In fact, let me just check. Is that both positive? Okay, good. And are they both, is one, 5 times bigger than the other? Yeah. And are they separated by 5? Yeah. Okay, good. And so that has to equal to 1 over F. And so grabbing a calculator here, I've got the 6 1/4 reciprocal added to 1 1/4 reciprocal, enter. Taking the reciprocal of that gives me a focal length of 1.0 4 meters. Good. So I would need a concave lens of this focal length, and I would need to place the object 1 1/4 away from that mirror, and then it would form an image on a screen that was 6.25 from the mirror, or another 5 meters from the original object. Yay!